limited specifically, I would say more in more priority would for the 2-qubit gates. It's there for single also, but 2-qubit gates is a bigger priority. Aside from this, you have error mitigation techniques also, and I guess you can tailor some of them to specifically work against C0 gates. Or again, that's a bit of a loose statement, but with techniques like error mitigation, right? So when we have a circuit, they say take zero noise extrapolation, for example. In this technique, again, we are going to do this mainly in the context of 2-qubit gates. We are not even bothered about the errors which will come from single qubit gates. What we do is in zero noise extrapolation is I know that if I put a C0, I put a C0 and then I put another C0, this translates to an identity operation. Okay. So what we do in zero noise extrapolation is first I take the normal circuit, I compute an expectation value from that circuit. Then I put two more C0 gates, because that's if I have, say, a C0 in the circuit, I'll put two more C0 gates that is going to operationally translate to just implementing a single C0 gate, but the noise will be 3 times more. Now I will do this for another circuit by putting two more sets of C0 gates. So where again it's operationally a single C0, but the noise is 5 times more. Now I will compute the expectation values from these two circuits also, and I will plot it. Okay, and I will try to fit that with a plot. And when I do, if this is going to be an expectation value against a noise factor sort of term. This is a very simple explanation of ZNE. There are a lot more details, but it's just to give you an idea of how this technique works. So if I look at the intercept on the y-axis, basically where the noise should be 0, I can potentially calculate the expectation value without noise. So this is just one technique, but as I mentioned, so the way to combat this exists in 2 levels. It exists in the transpiler step itself, even before you run your circuit, and then you can enable some error mitigation techniques to do it at the next level. Of course, there's more techniques that might exist at the hardware level also, but yeah, that's going to be a very involved discussion, and not all of it might be publicly known. So yeah, but there will be steps at the hardware level also to try to reduce 2-qubit gate errors, 2-qubit or just multi-qubit, and I mean consequentially multi-qubit gate errors as well.
Thank you so much for answering the questions, Janani. Now, in the interest of time, we'll now move on to the coding session.
Yeah, sure. So I mean, we don't have much time, but at least I'm going to be doing a live coding session, but this will help you guys to at least get started. There was a notebook, I mean, which was provided for Qiskit 101, and it's very self-explanatory. So I don't want to follow that exactly. I'm going to do a live coding session instead, because when we realistically program or code, right, where do we start? We start with a blank notebook, right? And sometimes there's steps even before you get started on a notebook that may not be clear. So that is why I wanted to do it live and do it from scratch. So my aim is to just show you how to simulate a basic circuit and say create a general GHZ circuit, which is we all know about a Bell state circuit. I think it's very it's one of the more fundamental things that people might have come across. So we will look at how to create like basic circuit, Bell state circuit, and the generalization in n qubits, which is the GHZ state. And further on, if you want to work forward from there, you can go back to the Qiskit 101 notebook. As I said, it's very self-explanatory in terms of how it's written. So yeah, I will leave that part to you guys, but now let's go to the coding session. Before we go there, I just want to, is my screen shared? No, right? Or is it?
No, it's not shared right now.
Okay, yeah. So let me share my screen. Very quickly, in 5 minutes, I want to show how you start building using Qiskit, right? Now I've come up with a quantum algorithm. How do I run it on a quantum computer? Now, using this 4-step framework called as Qiskit patterns, it's something that you can do. The first step would be to map your problem, right? So you map your problem instance to quantum circuits and operators. That is the very first step. And here, once you have mapped the problem, you will have to write the circuits using a quantum SDK like Qiskit. So from start, your input is going to be the problem you want to solve, and your output should be the solution which you want to get. You should have a way of post processing the results and interpreting them to get what you want. So that's the very first step, is to map everything to quantum circuits and operators, and basically write things using Qiskit. Then you optimize for target hardware execution, and this is done using a transpilation step. Okay, and there are other things also, but the main optimization can be done by is done by compiling your circuit to run on hardware. Then the third step is to actually execute it on hardware, and this is done using Qiskit runtime. Okay, and the final step would be post processing whatever results you get. So usually the results you get will be in terms of sampler counts, or execute or you will have estimator based expectation values. So then once you get it, you will have to post process and interpret your results. Okay, so for this, the input will be domain inputs. It could be some particular protein structure prediction problem. It could be portfolio optimization. But then you will have inputs here, which depend on the domain of the problem you're solving. The output should be circuits and observables, which are built using the Qiskit library. Then, if in the next step you take circuits and observables as the input and you transpile them, and your output should be an ISA circuit and ISA observable. Now, why is this the case? Because a lot of times the observable which you are working on should match the layout of that should match the layout of the circuit. Okay, and then in the next step, we use things called primitives. As I mentioned, there are two primitives, sampler and estimator. So you can either get things in terms of counts or samples, or expectation values. Here the input is ISA circuit and observable. And finally, you can post process your results doing things like error mitigation, or you can kind of do a visualization of your result to translate back to the domain specific problem you are solving. So the input here would be an expectation value or sample, and the output would be data objects or visualizations. Now you have more things on top of this as well. So there are Qiskit add-ons which build on Qiskit SDK. The main Qiskit ecosystem consists of Qiskit, which is the Qiskit SDK, which is the main package. Then you have Qiskit runtime, which helps you talk to quantum computers with the quantum circuits you've built using Qiskit. And you have Qiskit add-ons, right? So these are some of the Qiskit add-ons you can use to improve the result of what you're doing. So I'm not going to go too much into detail there. But essentially, how do you unlock the research? It's quantum software plus Qiskit plus QPUs, and that translates to useful work. Now I'll come to this after showing the coding part of the journey. These are just some existing resources. Okay, but yeah. So first step. Okay. Now, sorry about that. Let me just stop sharing for a second. Okay, so the first step would be to have a blank notebook, right? You need some kind of a text editor interface. Here I'm using VS Code. You could also use a Jupyter notebook. This is a Python notebook, IPYNB, but I'm using that via a VS Code. So before you start doing any programming, you need to know what are the three main packages you need to do like whatever you're doing. Of course, when you have domain specific problems, you can install packages related to that for mapping your problems. But say in this case, my aim is to just create a Bell state circuit. Okay. Oh, sorry, this is not a markdown, but oh, it is a markdown. Okay, so say my aim is to create a Bell state circuit. Now, before I run anything, I need an environment. I'm going to create a virtual environment so that I can run it specific, like, I can install packages and just manage my whole workflow well. So how do you now, again, a prerequisite is that you need to have a version of Python installed. Here I have created a virtual environment using Python 3.12, and I'd recommend going for Python 3.11 or 3.12. Up from 3.9 it is supported, but go for 3.11 or 3.12. That works best. So once you have Python installed in your system, you can just say Python mvenv and give a name for your virtual environment. Here I've given QFF IISc venv. Basically, so that's the name of my virtual environment. And once you press enter, you will be able to create it. Okay, now you have to activate this virtual. I'm okay. I don't have to activate it here because now I can just select this particular virtual environment to run things. But if you want to install things here, you can do it. You can also do it in this specific notebook. I'll do it in this notebook. Drawing your quantum circuits. So let me also install these. It's very quick, so it's done. Now I will just restart my kernel. So now I will say import numpy as np, import then I'm going to implement import. So first let me import Qiskit. I've imported all these packages. Let us just check the version of Qiskit we have. Okay, can so say pip show Qiskit. So this is Qiskit 2.2.2. It's one of the more recent versions of Qiskit that I have. I can say Qiskit IBM runtime. The reason you want to be aware of this is 4.43.1. Again, this is the latest version. The reason you want to be aware of this is because sometimes some bugs you might run into will get fixed in the latest version. So keep an eye on what version of Qiskit you're using always, and highly recommend do not go don't use Qiskit less than Qiskit 1, Qiskit 1.0. Best thing to do would be to use Qiskit greater than 2. But if you are using, don't go below 1. That is my recommendation, because you will again run into package conflicts. There's a lot of issues that you will be running into. So keep that in mind. So now how do I build a very basic quantum circuit? Sorry, is there something? Is there something? Okay. So, all right, we're starting from this blank notebook, right? So, how do you know what is there? So, another essential skill I would really recommend you guys to have is to be able to look up the codes and like basically learn. This is the Qiskit GitHub. So here exists all the code that when you say pip install Qiskit, you're installing this whole repository, right? So you need to, it's a really good skill to have, to be able to look up from the Qiskit repository and also the documentation. Again, because the hardware advances at a very high pace, a lot of changes might come in, and when you want to know how to implement the latest versions of everything, it's an essential skill to have to know how to look up documentation. Okay, so most of what you're looking for will always be available here. Of course, you can do, web browser based searches, but this is very important if you want to implement. And this is, so if you, first you need to also make an IBM Quantum platform account. The way you need to do it is mentioned in the Qiskit 101 notebook, which again will be provided to you. But once you log into your IBM Quantum platform, you need to create an API key. Then you need to create something called as an instance. So here, if you say we view all, initially you won't have anything, but you have to say create instance and create your instance. If you want to create an open instance, you need to be careful not to go choose a pay as you go option. If that's what you want, that's fine. But if you want to create an open instance only, make sure that you choose that carefully. Now in the platform, you will find you will find links to documentation and also learning, which hopefully I will talk a little bit about before I close the session. But here, this has a myriad of information, useful information, which will help you upskill yourself without any external input. It's very intuitive, and these are all YouTube style, these are all like video lecture style courses, so with some implementation in addition, so it will be really helpful to you if you explore that platform. So this is a hello world sort of implementation, and this is the Bell state circuit. Okay, so Bell state circuit is a 2-qubit quantum circuit, and you have it consisting of a Hadamard and a C0 between 0 and 1. And basically, as we discussed earlier on, like with just Hadamard, you will have a uniform superposition of 1 by root 2 0 plus 1 by root 2 1. But with like the C0, you will be able to create a state where you have 1 by root 2 times 0 0 plus 1 by root 2 times 1 1. So you don't have any intermediate states. So yeah, so here now we are going to see how to implement this particular how to implement this circuit in using using Qiskit. Okay, so first, to create any quantum circuit object, I can simply say quantum circuit of 2. But now let us first see what an empty quantum circuit looks like. Just say MTL. So this is an empty quantum circuit. Now here I have Q0 and Q1 with 2. These are called as wires. So if I say 3 instead of 2, I'll have 3. Now I can also create a quantum register which is more involved by adding some classical registers to measure. Now when I'm running a quantum circuit, I need classical registers to measure the state of my quantum circuit. So I can create a quantum register separately and a classical register separately. I'll have to import this here, but in the interest of time, I'm going to skip that. But you can just say quantum register, classical register, and you will have to create them separately. And a quantum circuit will be a combination of the quantum register and the classical register. Now, because we want to create the Bell state circuit, let us go back. So first we will implement a Hadamard on the 0th qubit, and then we will implement a C0. So now I have a Hadamard and a C0. But can I just run this circuit as is? I need to measure it, because now I say QC and measure all. So now this helps. Now this is called as a barrier. Now using a barrier is to it helps to when you transpile a circuit, it stops you from across a barrier. You won't be optimizing a circuit, so it automatically implements when you add a measure. So this is how you create a Bell state circuit. Now let me also show you how to create a GHZ circuit. So a GHZ, so okay, let us no, before that I should show. Now I'm going to run this on Qiskit Air. because it takes more time. You can implement this on hardware as well. The instructions to that will be shown in this notebook, which you can take a look at. It's very verbose. It's a bit verbose to explain during the lecture, but it's very detailed and a great resource to work through as a workbook yourself. So yeah, it's detailed with like many explanations and things in more things which are more basic, like how do you create a single state, how do you manipulate a single state, and the like. So yeah, here, but in this case I want to and you can also run it on your on real hardware. So here I'm just running it on a simulator for demonstration purposes, to show what the counts look like. So I'll say Qiskit simulator is this thing, like um, uh, two brackets. Then I just run the QC with a number of shots, and directly I can get the result. It might be better to say job and say job dot result. And then you can get the counts, and let me print the counts. So as you can see, this creates a 0 0 and 1 1 in uniform superposition. So similarly, if I want to create a general GHZ state, how can I do that? Oh, I'm going to do this very quickly because we are, I think, almost out of time. But we'll say QC1 is equal to, I can just use QC quantum circuit of N. And I will just use you can use a list comprehension also here. So yeah, I need to measure it as well, and then you can return QC1. So here to create a simple, if I have n qubits, I just need to add n more C0 gates, and I will be able to implement a GHZ circuit. So now I will say QC2 is equal to GHZ of 8 and QC2 dot draw. What does this look like? So this is just the normal print style drawing. If I want to have it in the pretty way, I can say MPL, which basically stands for matplotlib style, is equal to 0.5, let's say. So this is a general n qubit GHZ circuit. So let us just quickly run it, and then we will be done. Yeah. So as you can see, it creates a state like this. So yeah, with this I will kind of stop the live Qiskit coding session. I had other things planned, but like this is I would say very simple sort of entry point to understand how you can create circuits. Take a look at it in much more detail, because it's a really good resource to understand like everything from scratch and explore how to manipulate quantum states. And oh, sorry. Yeah, let me just go back to the PPT for 1 second. I just want to show. So as far as resources are concerned, how can you be a part of this journey? There's IBM Quantum Learning, which I just referred you guys to. So please go and explore what resources are there. There are also things like the Qiskit YouTube channel. There's events like Qiskit Global Summer School, of course, this Fall Fest. And then there's Developers Certification and Advocate, Qiskit Advocate, some of whom I think are also present in the members who are organizing this event. So please be a part of the IBM Quantum community. Also, the summer internship program, the applications are out now for 2026. This is the picture from, these are the interns from class of 2025. Some of you guys are here with us. So on this positive note, I would like to invite you all to apply, and thank you for your interest in quantum computing.
Thank you so much for that insightful talk, Janani. That was really enlightening and gave us a lot to think about. We truly appreciate you taking the time to share your expertise with us. So there was a request from participant that whether you will be sharing the notebook with them?
Yeah, sure. I will
And
be
there
sharing
is
the notebooks.
okay. And there was another question that whether you will be sharing the slides.
Yes, I'll share the slides for sure.
Okay. Thank you so much, Janani.
Thank you, everyone.
Now we head off to the next talk by Dr. L. Venkat Subramaniam. So, Dr. L. Venkat Subramaniam is spearheading India's quantum revolution with 150 plus research papers, 34 patents, and 3,000 citations. His best selling book, Quantum Nation, simplifies quantum computing for a wider audience, making complex science accessible to all. As an IIT Delhi PhD and a TED speaker, he bridges the gap between cutting edge technology and public understanding. Recognized with the IBM Outstanding Technical Achievement Award, IBM Master Inventor, and IBM ISA Growth Agenda Award, with groundbreaking work drives innovations and shapes India's quantum future, inspiring the next generation of innovators. This talk was given at a TED event using the TED conference format, but independently organized by a local community. So the stage is yours, Venkat.
Thank you. Thank you. Nice to see you here, Dibarati. So, do you want to take a break? I saw you've been here for 2 hours or whatever. So, I'm happy to just wait if people want to. What do you suggest? Or we start? What do you?
We can continue.
Okay, fine. Let's continue. Okay, so good evening, everyone. It's a pleasure to be here. So my talk is going to be more to give you an overview, okay, a landscape picture of how quantum is evolving, how India is placed in it, and what can be your roles, okay. So that's really what this talk is going to be about. So we have about an hour, right? Is that correct or? Okay, I'll assume it's an hour.
We are left around 1 hour.
Okay, perfect. Thank you. Okay, so I'll start sharing my screen here. Okay, just give me a second. I think you can see the screen. Okay, and it'll be nice if all of you are able to maybe, I don't know, can you put things on chat? If that'll be great. Please put chat. Please use the whatever those things are in between, which allow you to put emoticons and things like that to make it, interactive and for you also to just be involved in this. So I'll assume, you know a little bit about quantum, but as I said, the goal here is to give you that landscape picture of where quantum is headed. And I'm calling this the quantum decade for India. Okay, for us as a country, for us to leapfrog, for us to take the lead. So that's the goal here. So many of you probably already know quantum, the language that you use to program quantum computers are the same Python, C, all of those languages which you already know, right? So when you write your program in Python on a normal computer, the compiler compiles it into a string of zeros and ones, which is what the processor, the classical processor understands. But on quantum, this Python program of yours actually gets compiled into a quantum circuit, which then gets executed on a qubit, right? On a set of qubits, which you have. So in terms of the access, or in terms of the engagement itself, there isn't too much difference. It is the same programming languages, higher level languages that you are aware of. So the entry barrier is not very high. Okay. So each one of you can actually start right now to get your journey started. You all heard Janani. It's, you can access quantum computers over the cloud and you can start programming right away. So the goal of this Qiskit Fall Fest is for each one of you to start your quantum journey if you have not, to be able to, start using these quantum computers, even if you don't go very deep into it, at least start and start your journey. Okay, so that's the point. And I'll also give you one homework, which is that at the end of this week, I'm sure you all use Wikipedia. I don't know how many of you have edited things in Wikipedia, but at the end of this week, go on Wikipedia, pick any quantum related topic that is there, and please contribute one line, just one line, out of whatever learning you have this week. Okay. So as you go through the Quantum Qiskit Fall Fest, I'm sure you're going to learn a lot of things. And the point I want to make is that it's great, take knowledge in, but what are you going to do with that knowledge is equally important. And of course, I want you all to write a lot of programs and solve a lot of problems. But one simple thing, please go to a Wikipedia page, add one line. I'm sure there are things which people are not aware of, and you should be able to add that one line. Okay, so please do that. Now, there are some very special things happening in India. So these are the new and planned on-prem installations in starting from 2024, leading up to 2026. So as you can see, there is a system, the IBM Quantum System 2 is coming to the Quantum Valley Tech Park in Andhra Pradesh, India, in the first quarter of 2026. And with this, India will become one of the few countries with an actual performant, one of the state-of-the-art quantum computers, an IBM System 2. And which means, you're going to get an opportunity which very few people in the world have, which is to actually have a quantum on our soil with which you can access. Okay, so I'm sure, of course, you can access quantum computers right now also over the cloud, as I said, for free. 10 minutes of QPU time is free for every individual. Please use that. Please get started, as I said. But there is a system which is landing in India very soon. And this is actually one of the two in the world where there is also a government partnership which is happening. Okay, where the government is coming together, there is a public investment happening to ensure that the quantum system has wide usage and people are using it to solve local problems. People are using it to build things which will create a economy, a quantum economy. So IBM and TCS together have partnered to deploy this system too in the Andhra Pradesh Quantum Valley in Amravati, in the new capital that they are building. So you all know Qiskit. So Qiskit is the the SDK or the software stack which enables you to interact with the quantum computer. About 70% of the people across the world use Qiskit as the programming language. And now Qiskit development is also a large part of it is also going to be happening out of India. So, in fact, we are already hiring people for Qiskit software development. So, of course, they was part of our team this summer, and we are looking forward, as Janani pointed out, the call for internships for next year is also out. So please come join us to build the future of quantum. Okay, so Qiskit is the one that enables you to build applications, to run your algorithms, all of that on a quantum computer. And as I said, this development is moving to India now, and there is a big opportunity in front of each one of you. And Qiskit is open source. Okay, it's open source, which means that you don't even have to wait for anything. You can actually start contributing to Qiskit right now. Just go to GitHub, do some pull requests, solve a few of these existing, tasks which are there, and see if your solution can get merged with Qiskit. And I can tell you, that'll be a very, very, very proud moment for you, because that'll show that you are right now contributing to one of the most performant softwares available today for quantum programming. Now, what we are also trying to do is to get each one of you involved, okay? And this involvement can be at various levels. Like if you're a beginner, you could start contributing to Qiskit Air. If you're a middle person, Qiskit ecosystem. If you're very good, then you could do Qiskit add-ons. So the point is, just go there, solve some of the existing PRs, enhance some of the software libraries which are already there. See if there are new algorithms that you want to contribute. So we want to form a community here which is able to contribute at a world-class level. Okay. And this is an effort which we are beginning. Please stay in touch with us in IBM and see if you have interest, how can you contribute? Okay. So that's something which we are really eager to do along with you. So please do that. And if you do this, you already become world-class in your level of contribution. Okay, so this is something really, 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 important, which we are trying to start with the Indian student ecosystem, with the faculty, with research scholars, and everyone who is around. Okay, so see how you can do this. Bug Janani, bug me, bug Anupama Ray, bug Devarati also. She also is part of this very soon. So all of these are things that we want you to take part in and start contributing. So now getting into why quantum and what is so special about quantum. Okay. So you all know about supercomputers. This used to be the most powerful. Now it's like maybe 10, 11, I don't know what it is, what number. Usually the supercomputers, the best ones stay there for a few months, and then another one comes and pushes them out. But still, with all these supercomputers around, there are still lots of problems that remain unsolvable or will be never solved. For example, one of them is molecular simulation. Okay. Molecules, and caffeine is one of the sort of the smaller molecules of nature. It's present in coffee, for example. And if you wanted to model this molecule, it would take 10 to the power 48 bits to represent the energy configuration of just one fraction of a second. The energy configurations of the single caffeine molecule for a single fraction of an instant. Okay. And 10 to the power 48 is like 10% of the total number of atoms on Earth. Very, very, very unlikely we'll ever build a computer that big. And quantum computers with 100 and a promise of quantum molecular simulation. Why is molecular simulation important? New medicines, new materials, all of these things. New medicines take 5-10 years. New materials take 10-20 plus years. All of these are very, very tough to do. Why? Because today you take a test tube, take a diseased cell. In this test tube, diseased cell, in this test tube, you take the molecule, put them together. You see how that cell is reacting to this molecule, medicine molecule. Then you take it to rat, then you take it to dog, you take it to monkey, then man, and then you figure out, oh, this one has too many side effects. Sorry. Throw that molecule, start again with 2 test tubes. So all of these are big challenges which classical computers, because of that caffeine thing I showed you, are not able to simulate these molecular properties. So these are very, very challenging problems for classical computers in terms of how do you see reactions, how do you test the energy states. All of these are tough problems for classical computers, which they do not do. And that's where, as I said, quantum computers come in. They are able to show a path for us to try and solve some of these problems. So you're looking at accelerating the discovery of medicines from the current 5-10 years, bring it to a shorter duration. Materials, 20 years, shorter duration through simulation. The other one, the famous Shor's algorithm, 1994. Peter Shor showed what? Peter Shor showed that RSA encryption, which is based on prime factorization. Prime factorization, what are the prime factors of 15? 3 into 5. Prime factors of 100, 2 into 5 into 2 into 5. Now you take a very large number, a 2048-bit integer, and you try to do prime factorization of that integer number. Of that number into its prime into its integer factors. It takes billions of years on the best supercomputer. And so we use large prime numbers, multiply them, and use that as our key today to protect your passwords, to protect this WebEx call. All of these are encrypted using these large prime numbers and their multiplicants. Okay. So that's how RSA encryption works. But Peter Shor in 1994 showed that the problem which takes billions of years on a classical computer can actually be done in a few hours on a quantum computer. Okay, exponential speed up. That's what the quantum computer brings to this problem, okay, of factorization. And hence, since that day, we've been looking for new ways to encrypt our data. So now there are what are called post-quantum cryptography, where instead of using prime numbers, you start using numbers placed on a lattice. People are also looking at keys which are quantum, so quantum key distribution. So there are multiple ways in which people are looking at this problem. One is the classical post-quantum cryptography. You don't use prime numbers, but you start using lattice geometry to pick your keys. The other one is quantum key distribution, both of which people are now doing research on, and there are new techniques, new standards that people have come up with. The other is AI. So you're all very familiar with AI. You all understand AI. AI is about learning from examples. You give lots of examples and you learn from that. Now, in AI, there is a cat problem, as I call it. What is the cat problem? For you, how many cats did you have to see as a child to recognize cats? Maybe two, maybe three. That's it. And then you said, Mama, Billy. That's it. So the human, intelligence is able to do, infer from the data, store the data much, very, very efficiently, and is able to make very quick decisions based on very few examples. So you saw two cats and third cat comes along, you say cat. Now AI today for the same, recognition problem, cat recognition problem, requires thousands of cats. Okay, so which means, human, two examples, AI, thousands of examples, you now have, which means that you need to do lots and lots of, labeling of the data, because you need a lot of examples to learn from. Today's AI, you need to be able to do then, because the data is large, the number of features, everything blows up. Okay, so there is no, we do AI, of course, but the efficiency today is not what we really desire, because there is a benchmark, which is the human intelligence, two cats, and that's where you really want to go. And so the goal of quantum here is, and we are seeing evidence already, that AI, quantum AI, is able to bring it closer to the human. Maybe not two, but not 10,000 either. It's much closer, maybe tens, maximum hundreds. Okay, but an order of magnitude lesser. Okay, so I talked about three problems now. One is molecular simulation. The second one, we talked about factorization. The third one, we talked about AI. And each one of these has, quantum has solutions here, which are very, very promising. Some of them we have shown mathematically already as being, great in terms of, for example, Shor's algorithm shows that you can run it exponentially faster. So we know that we can reach there, and we are trying to get to those algorithms now. Okay. So over the next few days, I'm sure you'll learn about all these quantum phenomena and stuff, and already Janani talked about, and I'm sure you already have some knowledge. So what the quantum is doing, is that it is going beyond the limit of the bits. So with bits, we have been simplifying nature into zeros and ones. And that has been a problem, whether it is in AI, whether it is in molecular simulation, in several of these problems, because we are trying to simplify something into a string of zeros and ones, we are facing a challenge in terms of complexity, in terms of time, in terms of energy requirements. You all know how much energy requirement is there in AI, right? Many of the tech companies are now going to buy nuclear power stations. And that's where the qubit comes in, and it has all these very special properties: superposition, entanglement, interference. And this is what, when Janani was talking about, these are the things she's looking to exploit. This is what you're trying to do, to utilize, and this is what Shore's algorithm really did. Shore's algorithm used these properties to speed up factorization exponentially. And that's what, so you have a problem, let's say cat classification, and what you want to do is in the quantum computer, you want to use these properties because you can't use these properties on classical computers. The bits don't have these properties. They cannot, give you these things. And hence, you run these programs on quantum computers, but you also write algorithms where you are utilizing these quantum mechanical phenomena. So that's what quantum mechanics is about. That's what quantum computing is about. It's about using these properties and then taking your Python or Qiskit program and running it on the quantum computer. Okay, so that's what it is. Do we have questions? I mean, I'm happy to take questions. I don't know how you can ask here, maybe on chat or whatever, but please feel free to ask questions. Okay. But does this mean that we are going to replace classical computers? It does not mean that either, because there are many things which classical computers are very good at. For example, multiplication is much faster on a classical computer compared to a quantum computer. So, quantum computers are there for certain tasks. Classical computers are good at certain others. So, the future is CPU, GPU, and QPU working together. Okay, so you are going to have, even today on your laptop, typically you do not have GPUs. So, when you want to run your AI program, you run on the GPU which is sitting on your IISc cloud or whichever cloud it is, but it's usually not sitting on your laptop. Okay. So the same way, the QPU is also not going to be sitting on your laptop, not on your local system. It will be sitting somewhere on the cloud. And as I said, that system could, even next year, it could be sitting in Amravati, it could be sitting in New York, it could be sitting anywhere, but you will be able to access, just like you can access GPUs today. And already you might have seen a lot of the applications that we are seeing today are hybrid. People are using quantum and classical together to solve some of these problems. Okay, whether it is molecular simulation, whether it is AI, in all of these problems, people are beginning to use hybrid techniques to solve these. Now, this is the roadmap. Don't try to read it. 2016, 5 qubits. 2025, 156. 2024, 156. Now, later this year, IBM will announce its latest. And by 2033, we are going to reach 1 lakh qubits. Okay. And there are some very good milestones in between. So 2029, you will see the first error corrected qubits available. So by 2027, you will have 10,000 gates. By 2028, 15,000 gates. By 2029, 100 million gates, 200 logical qubits. And so what is happening is, just like there was a Moore's law, doubling of processing power every 2 years or 18 months, in quantum also we are seeing a similar exponential growth in the way the quantum computers are able to process. Okay, their processing power is doubling every year. So, which is very exciting, and which means you have a great opportunity. 2023 quantum utility was shown. What is quantum utility? Quantum utility is where you are using quantum computers to show that they are able to run problems which are beyond the ability of quantum and ability of classical computers. Okay, you're able to do problems which you are not able to do on classical computers, the best classical ones. So there was this Nature paper which came out 2023. Quantum advantage. What is quantum advantage? Quantum advantage is where you are now able to run these things on quantum computers, but you're also able to solve some real world problems and getting to show that, you're getting to a point where you're solving something much faster, much more cheaply, or much more, uh, you know, um, accurately in terms of what you are able to solve. Now, the big question is who is going to bring quantum advantage and when is it going to happen? So, okay, so when is it going to happen? Well, at least IBM has said it will happen in 2026, which is like next few months. So, already you would have seen a lot of announcements happening where people are saying, we have reached quantum advantage on so and so problem. And so what's going to happen is in the next year, next few months, next few years, you're going to see an acceleration in the in new results coming out. People are going to be every week, they're going to announce some new result saying, look, I have reached quantum advantage. About 2 weeks back, Google claimed quantum advantage on a problem. 3 weeks before that, HSBC and IBM showed that on a finance domain problem, you're getting 34% improvement over the current known classical techniques in algorithmic trading. Okay. Now, those are very, very, very exciting. Why? Because since that HSBC paper came out, we are getting every bank now interested. Now, I do know that a lot of these financial companies also come to campuses to recruit people. And very soon, they are going to be asking, okay, do you know AI? Do you know, financial whatever prediction and things? But they're also now going to be asking, are you aware of that HSBC result? Do you know what kind of advantage quantum brings to some of the financial domain problems? So, banks, financial institutions, their eyes have been opened now. Suddenly, they're all very keen to see that, okay, HSBC did it in this problem. What are the problems which I can bring quantum advantage in, or where I can show some improvement over existing techniques that I'm running currently in the bank? Okay. So that is one of the key things where there is a lot of interest now within industry because we're getting towards that quantum advantage point. And 2029, as I said, is the year when you will have logical error corrected qubits. And that is another big milestone because then what happens is that a lot of these, the applications that you will run, they will, you will be able to run them much more efficiently because of the error corrected qubits which will be available to you. Okay. So all of this points to the fact that all of you in your next few years, you're all still in college, but as you come out, as you graduate, you will be entering a world where for the first time there'll be two kinds of computers, two different kinds of computers. One is your bits zeros and ones. And the qubit or the quantum computer, for the first time in history of computing, is not an extension of your mobile phone or your laptop or your supercomputer, but it's an entirely new kind of computer using entirely new kind of computing at the base. The qubits are not using zeros and ones, they are much closer to nature in terms of how they process data. And that is what is going to give you that big advantage, okay, on certain problems like AI, like factorization, like molecular simulation, in all of these, right? And the big question now before you, the young people, is who's going to bring this quantum advantage? Can people, write on chat or something? I don't know. It'll be nice to interact if that is
Yes, there are
possible.
questions from the participants.
Okay,
So,
great.
one of the questions is, what are your opinions on a person pursuing interdisciplinary research on classical and quantum computing? Is it a good approach towards computing and trying to solve a complex problem? Kindly share your opinion in this. Yeah, so this is the
Yeah,
question.
thank you. Yeah, that's a great question because, you know, right now, the quantum computer has reached a point, but it hasn't reached a point where it can solve really complex problems, right? It has reached a point where it is able to, as I said, demonstrate some small value on some quantum, let's say AI problems, some molecular simulation problems. But the big advantage is really going to come from the hybrid techniques where quantum and classical come together. So, for example, in IISc, Professor Yogesh Simhan is looking at hybrid techniques, quantum plus classical, on chemistry problems, on optimization problems, because quantum computers are still at their beginner or the infant stage, but there are some problems which they can solve very well. Okay. So you don't want to solve your simple problems on the quantum computers, which you are already doing well on your classical. What you really are doing is, given a big problem like this, you are breaking it up into 10 different parts and you are saying, okay, these five run very well on my classical computer, on my GPU or on my even CPU. I will run these five problems or the five sub problems. Uh, think of it as an AI problem, for example. The kernel estimation could happen quantum, for example, the boundary estimations. The rest of the feature extraction, all those things can be on the classical. Okay. So, what you want to do is out of the 10, you want to see which ones are good for me to run on the classical computer, and then which are those two or three or four which are very hard for the classical, and how can I speed up those operations on the quantum computer. And that is how, you might have, I don't know if you've seen, but there are some recent papers on molecular simulation where they do exactly this, where some parts of the problem is running on the classical, some part is running on the quantum, and then you combine and give the final result. Okay. So that's where the world is running. And in fact, in IISc, some of the cutting edge work in this is happening. Okay. And you also asked about domains. What we are seeing is now that, there was a time like 2, 3 years back when everybody wanted to do computer science. But right now, in the quantum world, the physics people are needed, the chemistry are needed, the maths are needed, the electrical engineers are needed, the mechanical, the civil. So it's a truly interdisciplinary area where you're seeing the convergence of many people coming together. So, for example, I was recently in Andhra in a university called Rajiv Gandhi University of Knowledge and Technology in Srikakulam. So there the director was showing me some problems about the structural properties of the bridge. Okay, the bridge. You have the bridges, steel bridges and all that. So how they see whether the bridge is in a good state or not is through some, you put it in some resonant frequencies and then observe and measure and all of that. And those things are very, very complex to do. Then in Vizag, you have the DRDO lab, which makes torpedoes, submarines, and ships. Now, for a car, Maruti, for example, has a wind tunnel in Gurgaon where you run your car through it, you measure all the aerodynamics of it, and you say, okay, great, this design is good, or you say, I need to change this design like this. Now, for submarines, torpedoes, and ships, yes, there is a underwater test range in Cochin, but you still need to simulate because you can't do much underwater. Too many things can't be done. Now, simulating 1 cubic centimeter of space on the best supercomputer takes hours. So imagine a torpedo moving like this for 2 or 3 meters. How many months is this going to take, this simulation? So these are examples where mechanical engineers, civil engineers have been struggling. They have not been able to measure some of these things. They've not been able to predict. Another problem, the civil engineer people told me was dams. You keep hearing about floods in India. There are dams. If you don't open the dam gates, the upstream gets flooded. If you open the gates at the wrong time, the downstream villages get submerged. So, what is the right time for you to open these gates? When should you do it? And when you do open it, what is going to be the path of that water flow going to the downstream villages? All of these are civil engineering, mechanical engineering, computer science, all of that coming together. And they cannot be solved on the best supercomputers today. And so many of these people are now looking at how do you take a quantum computer to solve some of these problems. And quantum advantage is really about taking these very tough problems and trying to solve them. It's about saying that, look, I can solve the flood problem to some extent using the quantum computer. I can solve the CFD problem for the torpedoes using this. Now, the big question is, who is going to bring quantum advantage? Devarati, any more questions?
Yes, there is a question. So, what about quantum hardware? How to work on physical QPU design? How to get knowledge, internships in quantum hardware?
Very nice question. Okay, so we will come to that. Okay, so now that's an excellent question. Please keep it in mind. Now, in quantum, where is the talent? The talent is actually sitting right here in India. You are that talent. The biggest talent pool in quantum sits in India today. Okay, whether it is in terms of the right graduates with the right skills, or even in terms of the usage of the IBM quantum computers, those 10 free minutes which I talked about. India, US, India, US. Okay, so that's how it goes. Qiskit Fall Fest, the maximum applications came from India. Okay, so there is a huge talent pool sitting right here in India, all of you. And now the goal of the government is, where is this quantum advantage going to come from? And that's why the National Quantum Mission, NQM, was announced in the year 2020. Cabinet approved 2023 a budget 6,000 crores money released or getting released, lot of proposals getting funded. And IISc Bangalore is the quantum computing hub. IIT Madras is the quantum communications hub. Uh, IIT Delhi is the quantum materials hub. And IIT Bombay is the quantum sensing hub. Now, and there are multiple other institutions, okay? ISRO, there are also private institutions like TCG Crest, like BITS Goa, and others who are also looking and working, okay, in this. And they are getting funded at this point. And this is just the first round, okay? And the first round of funding, all these institutions that you see here, they were all funded for hardware. So the question that you asked, okay, in terms of where do I start doing hardware? IISc Bangalore is a great place to start doing hardware. You are going to get some of the best central facilities in the world. It is already getting set up. Some of it is already sitting there. So, for example, Vibhor or Baladitya Suri or Dr. Chandrasekhar, they are already working on these things. They have quantum labs, hardware labs where they are building things. So please just keep your eyes and ears and everything open and just go around, reach out to these institutions because they are looking for interns, they are looking for JRF, they are looking for SRF, all kinds of positions. Okay. In addition to this, now this is academia, right? There are these 43, but there are many more also, which are very keen. Government is also setting up 100 labs across the country in different institutions. Quantum labs, hardware labs, okay, hardware labs. Yes, it's going to take some time, but you can immediately start your journey, okay. One is, of course, the software part, which, we are covering a lot of it. Janani covered a lot of it. But there is also the hardware part where, again, for example, if you wanted to design a quantum processor, there are packages, open source packages like Qiskit Metal, which you can use to design your processor. And there are fabs around the country where you can go to, like IIT Bombay, even IISc Bangalore, where you could think about how do you tape out your design. Okay. So in terms of the future, there are lots and lots of opportunities across the stack, whether it is hardware, whether it is middleware, whether it is software, whether it is different kinds of technologies like communication, sensing, materials, computing, or whether in computing you are interested in photonic computing, you are interested in diamond envies or superconducting or ion traps or neutral atoms. All of these are areas which have already begun, and they are certainly looking for people like you who can come and join them and help them. But I also get a lot of applications from students like you. So there is one class who says, I have done it. Venkat, look at my GitHub. I have done this many PRs. I have gone and solved this many problems. You can look at my GitHub. Then there is another class of people who say, I'm great. I have great knowledge in quantum computing or quantum mechanics. I've done great in my courses. And if you give me a chance, I will prove myself by doing things. Now, which category of students do you think we start hiring? We start hiring those who have done something. Those who don't only say that I have knowledge, but those who say that, look, I have knowledge, and I've used that knowledge to show and populate my GitHub. I've gone and talked to this professor, and with that professor, I've worked on this problem and solved this. So please be that person who takes that knowledge, but also takes knowledge and transforms it into something usable, into some hardware or software or product or solution which people can use. Okay. Does not matter if it is a if it's not perfect. Nobody, in fact, nothing is perfect. So please start your journey by building things. So the person who asked this hardware question, there are all these institutions, but there are also startups. The National Quantum Mission is also funding several startups. Many of them, in the first round, they funded 8 startups with up to 25 crore funding. And many of these startups are hardware startups. Okay. Many of these startups are doing hardware, whether it is in communication, sensing, materials, computing, all of these. And the second round of selections are going on right now. And in fact, many of these startups are by students like yourself. Some students coming together saying, look, I tried to solve this problem during my college days when I was in my project year. I tried solving this. I got up to this point. And now I think I have something which I can work on and make that into a product. And often the faculty are also joining together. So you have faculty and students coming together to solve some real problems. Okay. And that's how many of these startups are getting formed. In the first round, there were 100 plus applications from 100 plus startups. 8 of them got selected, as I said. But, if you have ideas, startups are there to, is one channel for you to build something. But if you don't want to found a startup, that's okay. These startups are also hiring. At any given time, you can contact all of these startups and they will be very, very, very happy to have somebody like you join them. But as I said, don't just go with your course knowledge. In addition to your course, do some real building work, build a system, hardware or software or whatever, but build it, because that shows your initiative. It shows that you not only are a learner, but you are a learner who takes that knowledge and builds things out of it, makes things out of it, uses their hands to do things. In addition, there are also a lot of courses which the government is starting, a lot of labs are getting set up, as I said. So a lot of this is now pointing to an ecosystem which is beginning to thrive, where people are starting to create jobs in academia, in startups, in industry. So I don't know if you've been following the news, but a lot of the industry is also trying to come in. And by industry, by startup, I mean somebody who is just beginning, taking some VC money and all that. By industry, I mean people who are already established industry players who build products, who sell products, and who have some revenue or things coming. And they've been around for a few years now. Even those have now entered this space. So, whether it is in hardware or software, there are multiple opportunities. And even, the classical world, whether it is banks, after the HSBC announcement, all the banks are now saying, do you know any bit of quantum also, in addition to the AI and in addition to your data structures and whatever else through your courses? How much of quantum do you know? Okay. And that question, more and more industry is going to begin to ask you as you enter the job market. Okay, any other questions?
I think the explanation explains a lot of questions that were in the chat.
Okay, great. Very nice. So yeah, so we'll move a little bit ahead. So as I said, quantum advantage. People are now searching for that quantum advantage. And I told you the talent is sitting in India. And which means that quantum advantage needs to come out of India. Whether it is hardware, whether it is software, any of those things, this is where the talent is. And in the past, what has happened is, yes, we had a lot of talent in the past also. Father of Pentium, Vinod Dham, father of fiber optics, Kapani, all of them came out of this educational system of ours. All of them were students in IISc, IIT, and today you have many of them as CEOs of these very large companies like Microsoft, and some of them are even from tier 2 institutions. So all of this says that we've been doing great in talent, but this time not only do we want to build talent, but we also want to build the corresponding industry here in India. We want to build the uh, you know the industry, the economy. And yes, last time talent was there with in the computing era when it began in the 70s, 80s, 90s. India was a poor country. So yes, maybe we could not invest that much that time. So everyone had to go abroad and build their careers. But now we in 2025 we are a middle income, low to middle income group with an aspiration to go to a advanced economy by 2047, next 22 years. Okay. And these years are critical for us in terms of using the talent that we are creating here in India, in IISc, in our top institutions, even in our tier 2, tier 3, tier 4 institutions, and make sure that we build the future industry right out of here. Okay. And I'll give you examples. For example, the PC came out which year? 1970s. Who made PC useful? Microsoft. What did Microsoft do? It created the operating system and it created all these tools like Excel and all of that. It was only after that that you and me all started buying personal computers. Internet came in 83, but people would buy PCs, but they wouldn't take internet. They would say, what do I need internet for? I don't want to spend money on internet. But then came along Netscape. Netscape created the browser. Before Netscape, we didn't know how to go to a website. And then came Google. Google said, here, I know how to search data for you. So before that, if you wanted to go to the website of IISc, you didn't know how. You had to remember, IISc.in. Whatever. After Google came, you could just type IISc and you could go to IISc website. So that gave a big boost to internet. For about 10, 15 years, internet was just sitting in the labs. AI came in the 50s, 60s. It had been sitting in the labs. Only OpenAI came and made it useful. ChatGPT said that now every little child also starts using AI. Now, that quantum advantage we are talking about is one of you forming the Microsoft or the Google or the uh, OpenAI of the future who's going to build out those applications which make quantum useful. Okay. And that's what National Quantum Mission is all about. That's what this funding to institutions like IISc is all about. That's what funding these startups is all about. It is to ensure that our talent is able to create these things, right? And a lot of that work has already begun. For example, this is work with IIT Madras. I think many of you know last year's Nobel Prize in Physics was for AI, but so was the Chemistry Prize. Chemistry Prize was for using AI to predict protein structures. But as you know, not all protein structures are known, so AI does not have examples to learn from. And that's where quantum comes in to predict protein structure without where you don't from basic physics principles, basic chemistry principles. How is a protein going to fold? Because that folding is very critical, because that's folding is what determines whether the COVID which comes into the lungs is going to go and fit in that lock and key mechanism and cause COVID-19. The protein inside your lungs is what matters. And the medicine is the blocker. So the structure really matters. And if you can't predict that structure, you can't create medicines, you can't create enzymes, you can't create many of the things that we do with proteins. Okay, even digestion is protein-protein interaction. So all of these things, we are trying to see how you can model. So how are we doing on time? I think we are out of time probably. It's been an hour, I see. So I think we'll just go to questions. I think you have a very exciting week that you have ahead. But as I told you, your homework, please don't forget your homework. You have to go to Wikipedia and add one line that you learned this week, whatever it is, something you learned. Pick any Wikipedia page on quantum and add your knowledge there. Lots and lots and lots of job opportunities opening up. IBM is hiring, TCS is hiring, Amravati, several companies are coming and hiring. Bangalore, Qiskit is coming, people are going to start hiring. A lot of the startups are hiring. There are opportunities in PhDs, masters, all of those programs also. Even the